In this video, we're going to look at the arithmetic of complex numbers. I just want to note first that complex numbers are composed of two parts. We have the real component, A, and we have an imaginary component that we call BI. So A and B are both real numbers, okay? So for example, 3 plus 2i. The 3 and the 2 are both real numbers, but the 2i itself is imaginary. And we have to remember that I is equal to the square root of -1. So let's take a look at the first example, which is addition of complex numbers. So when we're adding and subtracting complex numbers, we're going to treat the I a lot like we do X in our algebra problems. So in this case, we want to expand the parentheses. So this is going to become 3 plus 4i plus 2 minus 6i. Now we're going to do what we did in algebra. We're going to add or combine like terms. So we're going to combine the two real components, the 3 and the 2. 3 plus 2 is 5. And we're going to combine the two imaginary components, 4i minus 6i, which gives us minus 2i. That's our final answer for part 1. Now we're going to look at the subtraction of imaginary numbers, or complex numbers, which is just a little bit different. So here we're going to expand the first parentheses, so 4 minus I. This time we're subtracting the second set of parentheses. So when we expand this, it's going to be minus 5 and minus 11i. Okay, so that's the only part that's different here. When we subtract this parentheses, we need to expand it by taking this negative and distributing it into the parentheses. So now we're just going to add like terms. The 4 and the -5 give us -1. The negative I and the negative 11i give us negative 12i. That's our answer for part 2 for subtraction. Now we're going to do some multiplication of complex numbers, which is, again, a lot like just using x. So what we're going to do is we're going to have to use the FOIL method. We're going to do 2 times 6 plus 2 times -2i plus 3i times 6 plus 3i times -2i. So let's write that out. 2 times 6 is 12 plus 2 times -2i, so we're actually going to get minus 4i, plus 3i times 6 plus 18i. And now we're going to have 3i times -2i, which gives us -6i squared. So let's go back to our definition of I. I is equal to the square root of -1. So when we square I, we get the square root of -1 squared. So I squared is equal to -1. And that's going to be important in this problem. So what we're going to do is we're again going to combine like terms. We have -4i plus 18i. So that gives us 14i. 12 plus 14i minus 6. Now instead of I squared, we said I squared is equal to -1. So we're going to multiply by -1 instead. -6 times -1 is positive 6. Okay, so we have 12 plus 14i plus 6. Again, we add like terms. 12 and 6 give us 18. So our final answer is 18 plus 14i. In our last example here, we're going to do some division of complex numbers. And we're going to need a new term here, which is the conjugate of a complex number. I think the best way to define this is to give an example. So in this case, our complex number in the denominator of this fraction is 7 plus I. The conjugate of this complex number is 7 minus I. So for two conjugates, the only thing that changes is the sign in front of the imaginary part. So for example, if our complex number is 3 minus 6i, the conjugate would be 3 plus 6i. Now that's going to be very important in this example. So I'm going to rewrite this as 4 plus 6i, and now I'm going to just do a horizontal fraction, so over 7 plus I. So we want to simplify this so that we don't have any imaginary component in the denominator of the fraction. You see here we have an I, so we want to get rid of that. So whatever we multiply on top of the fraction, we can also multiply on the bottom, because that will just be multiplying by 1. So what I'm going to do is multiply the top and the bottom by the conjugate of the denominator, which we found right here, 7 minus I. So we're going to do 7 minus I in the numerator and 7 minus I in the denominator. You see how this here is just multiplying by 1? So it doesn't even affect the overall answer. All it's going to do is make it look a lot nicer. So in the top, we have a multiplication problem, 4 plus 6i times 7 minus I. In the denominator, we have 7 plus I times 7 minus I. So what we're going to do now is we're going to do what we did in problem number 3, where we FOIL out these complex numbers. I'm going to start that down here. So we have 4 times 7, 28. 28 plus 4 times negative I, so minus 4i, plus 6i times 7, plus 42i. Then we have plus 6i minus I. So, or times minus I, that's going to give us negative 6i squared. And on the bottom, we're going to have 7 times 7, 49, plus 7 times negative I, negative 7i, plus I times 7, plus 7i. Now we're going to have a plus I times a negative I squared. Now this is where we can see how important the conjugate is. On the bottom here, we see a negative 7i and a plus 7i. So we're going to group like terms, and those are just going to cancel out. That right there is the importance of the conjugate. Because what is I squared equal to? I squared is equal to negative 1. So as you can see, the denominator is going to be a real number. So let's simplify the top up here. We have a negative 6i squared, which is the same thing as positive 6, right? So 28 plus 6, 34. We have minus 4i plus 42i. So we're going to have plus 38i in the numerator. In the denominator, we're going to have 49 minus I squared. So this is just plus 1, correct? 49 plus 1 is 50. Now we can simplify this by dividing the numerator and the denominator by 2. Okay? Because we have a common factor of 2 in both the numerator and the denominator. So we have 17 plus 19i over 25. So we're almost there. We need our answer to be in the form of a plus bi. And here we have something in the denominator that sort of disturbs that whole setup. So what we're going to do is we're going to do 17 over 25 plus 19 over 25i. And that right there is our final answer.